Hello, this video will be introducing you to some concepts in regression and introducing some terminology that you will encounter as you work through the literature. It is my hope that you will use this to critically review papers not just for this class but throughout the PharmD program, in particular your pharmacotherapeutic problem-solving classes. So why do you need to learn about regression? Well, regression is very commonly used in the literature to study the association between a variable of interest and the outcome. Regression formulas can be easily adapted to take into account complex interrelationships that may impact your outcome. For example, controlling for smoking when you study the association between diet and heart disease. Linear regression is used to study the association between a predictive factor and a linear continuous outcome. Examples of continuous outcomes may be BMI, respiratory function measured in breaths per minute, total number of physician visits per year, or length of stay. The conceptual formula for linear regression is y equals mx plus b. This should be familiar to you as the formula for a line. M is the coefficient. This is how your dependent variable y changes based on your independent variable x. In the formula for a line, this is the slope of a line. B is the intercept. For an example, I'm going to walk you through these two graphs. The graph on the left is age of admission on the y-axis and birth date on the x-axis. The graph on the right is respiratory syncytial virus load on the y-axis and age in months on the x-axis. Here I show B where the intercept would be. M, the regression coefficient, is the slope. This indicates the change in y for every unit increase in x. In this hypothetical example, as the number of candy bars increases by 1, BMI increases by the amount of the coefficient. If the p-value and the 95% confidence interval for the coefficient are significant, then the association between the number of candy bars and BMI is significant. Here I'm showing you some real-life computer output that calculates the coefficient for the association between age in months and respiratory rate in breaths per minute. The intercept, or constant, is 54.6. The coefficient is negative 0.16. This means for each additional month of age, the respiratory rate decreases by 0.16. The respiratory rate in a newborn, then, who is 0 months of age, according to this linear regression, is 54.6, also known as the intercept. We can apply this equation to calculate the respiratory rate for other ages. The respiratory rate in a 10-month-old is the coefficient times 10 plus the intercept. The respiratory rate in an 11-month-old is the coefficient times 11 plus the intercept. Notice the number for the 11-month-old is lower than the number for the 10-month-old. This is because the coefficient is a negative number. Other types of regression include logistic regression and Cox proportional hazards modeling. Logistic regression measures the association between your predictor and a binary outcome. Mortality is yes or no, readmission is yes or no, etc. It is used in case control studies, but it's also okay to use for cohort studies as well. Logistic regression is very commonly used just because it's a convenient way to analyze binary outcome data. Cox proportional hazards modeling measures the association between your predictor and the hazard for the risk of an event occurring, including the time to event. This type of regression is used in cohort studies with variable person time. Logistic regression is used when you have a dichotomous outcome. Here is the conceptual model. Logit P equals the intercept plus your variable times its coefficient. This is calculated using a statistical program, and the results give you the odds ratio for the association between the variable x and the outcome with a 95% confidence interval and p-value. Cox proportional hazards model are used in cohort data when you have follow-up time. In this analysis, time until event matters. In other words, it is not only important that the person had the disease, but we also take into account how long it took them to develop the disease. Cox proportional hazards modeling calculates hazard ratios which are very similar to relative risks, along with confidence intervals and p-values. Multivariate regression models are regression models that are extended to look at the relationship between exposure and outcome, which simultaneously looks at the effect of other confounding factors. Remember the definition of confounding from earlier. Pause and review that video if you need to. Using multivariate regression models is one of the most common strategies for handling confounding in observational studies. A typical regression analysis is conducted as follows. First, an unadjusted model is created. This is a model that only includes the outcome and the exposure with no confounders included in the equation. The coefficient indicates the impact that the exposure has on increasing or decreasing the outcome. After the univariate regression is completed, a second regression equation is created. This equation incorporates the study's outcome. The main exposure here is shown as variable x, and potential confounders shown as variables y and z. The coefficient of x is used to calculate the odds ratio and the association between variable x and your outcome, controlling for the effect of your adjustment variables. Here is one real-world example of how you might see multivariate logistic regression models presented in the literature. We will practice additional examples in class. This is a study of how indoor tanning, the exposure, is associated with melanoma, the outcome. The odds ratio tells you the odds of getting melanoma in people who have ever tanned indoors versus people who have never tanned indoors. To get the crude odds ratio, the conceptual equation is melanoma equals odds ratio times ever tanned indoors plus intercept. To get the adjusted odds ratio, the conceptual equation is melanoma equals odds ratio times ever tanned indoors plus the adjustment variables plus the intercept. The logistic regression model will calculate a p-value and a 95% confidence interval for your odds ratio. This tells you if the exposure, tanning indoors, is significantly associated with the outcome melanoma. We interpret the odds ratio from the logistic regression model the same way as we interpret any other odds ratio. Less than 1 is decreasing disease, greater than 1 is increasing disease, and 1 is null. So, for our example, the crude odds ratio, which comes from the univariate unadjusted model, is 1.62. The adjusted odds ratio is 1.74. Notice that the crude's odds ratio and the adjusted odds ratio are slightly different. For the adjusted odds ratio, any effect of age, gender, etc. on disease has been accounted for in other places in the mathematical model. The adjusted odds ratio communicates the effect of tanning indoors independent of the effect of the other risk factors included in the adjustment variables. We could communicate these results in a number of ways. Here are some examples listed below. Feel free to pause and take a moment to read through them. Remember, we're going to practice some more examples in class. This concludes our video.